my name is Visser, based out of the Netherlands. I'm a group product manager here at Confluent, and I've been using and contributing to Apache Flink since 2016, so for the past 8 years. I'm a Apache Flink PMC and a committer. And throughout this presentation, I will use a variety of examples, and all the links to the various repositories that contain these examples are in the link tree, as you can see on screen. And I'll also show it at the end in case you want to take a look. I added a QR code so you can easily scan it, so you don't have to scramble to actually look what's happening in there. So what am I planning to talk to you about today? I want to give you a quick overview of Apache Flink and Apache Flink's table API. We'll dive a bit into the architecture of the table API, the capabilities, go through the examples, have a section on user-defined functions, and then at the end we will have the room for questions and answers. And by the end of the talk, I hope that you will understand the capabilities of Flink's table API, the architecture, and how you can actually leverage it for building efficient and scalable real-time data processing applications. So let's start with a quick overview. A brief introduction to Apache Flink. We have all sorts of systems that are producing events. You can have CDC events in your databases, your own applications, third-party applications, something coming in from IoT devices as measurements, mobile apps, you name it. And usually these all come from the operational part of your organization. And these events might power other applications like fraud detection, or perhaps you would like to know how many of these people have been logged in. And systems like Apache Kafka are used to stream these type of events. And Flink is an open source, unified stream and batch framework for processing events. It can connect to systems like Kafka, Kinesis, other systems like file system. You could connect it to Apache Iceberg or Hudi, and you can consume events in different formats from JSON to Avro, Parquet, and very much more, of course. So why is Flink a standard in stream processing? And there are a couple of main reasons for that. First off, Flink has an incredibly powerful runtime, and it enables high performance and scalability for any type of workload. Flink's runtime architecture is designed for, we call it limitless scalability, to allow you to process massive amounts of data. I think the largest publicly known use case or report on Flink out there has processed roughly 4 billion events per second and produced approximately 3.2 petabytes of data. So it's the scale of which Flink has been used has been incredibly massive. And Flink achieves that by parallelizing applications into possibly thousands of tasks. They are then being distributed and concurrently executed in a cluster. And that parallelization allows Flink to scale horizontally, meaning that you can add more machines to the cluster, but it also supports dynamic resource allocation so that you can allow it to adapt to changing workloads and allocate resources as needed to basically make sure that you're getting the right performance out of it. The second reason is its fault tolerance. Flink is able to handle failures effectively, and it's available as a high available solution. And it does so via its mechanisms of checkpoints and save points. It's basically a snapshot mechanism. And checkpoints are automatically created by Flink periodically, and they are used to recover from failures. They are specifically optimized for quick recovery, and they are managed by Flink, compared to save points, which are manually triggered and can be used for things like upgrades and everything else. The third reason why developers love it so much is because it has actually many languages to choose from. So you can use it in a Java version, you can use a Python version, you can use plain SQL in there. It has a lot of wide variety of built-in functions, so there is a lot of room to actually get the stuff done. And as I said, Flink is a unified batch and stream processing solution, meaning that you only need one technology to perform both. It allows a batch processing mode and a stream processing mode, meaning that your business logic, your SQL statement, your Java code, your Python code only needs to be developed once, and you can seamlessly use it against the batch source or a streaming source. It's actually the source that determines how your data is being executed. And you can choose between the different execution modes depending on the nature of your data, the trade-offs that you have to take in terms of, am I interested in real-time results, am I interested in incremental results, or am I actually interested in a point-in-time result? Most common example that I use is streaming mode is used in use case like real-time fraud detection. Batch mode is more for if you have generating financial reports on a daily, a weekly, or a monthly basis. So what is actually Flink's Table API? It is one of the APIs available in Flink's framework. And if we look at it in terms of abstraction, and we work our way up from the bottom of the diagram in the top left, we actually see process functions. And the process function in Flink is a primitive building block. It's capable of implementing basically any operation because you're directly manipulating Flink state backends and timer services. And at this level of the API stack, you are writing code that reacts to each event as it arrives, one event at a time. And technically speaking, process functions are actually part of the DataStream API, but in the DataStream API there are slightly higher levels of abstractions where you have building blocks that include access to things like streams, timers, and windows. And approaching to the top of this diagram, we find the Table API. And in terms of abstractions involved, it's easier to compare the Table API to Flink SQL. But as a developer, you're using the Table API, you're writing Java or Python code rather than using SQL. And one thing to note is that all of these APIs are actually interoperable. It's not that you must choose one and that excludes all of the others. In fact, there are quite a number of Flink applications out there that combine and go from one of the APIs to the other. Now the figure on the right actually shows how the code that's implementing these APIs is organized, where process functions are part of the DataStream API, and Table API and SQL, they share the same architecture, they very much work in the same way, and the entire operator topology is determined by the planner and the optimizer. And it's not that Table and SQL API are implemented on top of the DataStream API. In fact, they are two completely separate APIs, which offer the same capabilities and functionalities. And both, in the end, are built on top of the very same low-level stream operator APIs. So then, why would you actually use the Table API? And I think the most important reason for this is because it simplifies stream processing. You can use your language of choice, meaning Java or Python. And the Table API is a fluent API, and it's centered around table objects. You can define table objects programmatically, or you can define them with Flink SQL. As you can see here on the example, the first example is a programmatic example where we say from values, hello world, but you can also do a SQL query which you directly embed into the application. And when you submit a Table API application, what happens is that the optimizer improves the execution and the planner generates the job graph for you. The DataStream API basically requires you to define your own job graph, your own topology in there. You need to define things like how state is being serialized in the operators, how the connection between the different operators works. So you are very much more responsible for making sure that your application works as expected. And what we often see is actually that people start out with the DataStream API, but shoot themselves in the foot somewhere along the way, and they actually are getting stuck. So internally, the Flink Table API engine works on binary data, and it executes your stream processing application as efficient as possible. So there's no own state serializers, there's no chaining of operators or anything like that compared to the DataStream API. And conceptually, we have the idea of a table in the Table API, but under the hood, it's very much a changelog processor. And for that, I need to make a quick sidestep about stream table duality. I have an example here where I have an orders table. I have a query that is going to sum up the total amount ordered, and I'm going to sync that in another table, which is my bestsellers table. And this SQL statement, of course, is doing an aggregation, and therefore the result is an updating stream rather than an insert-only stream. If we look at the orders example, the first two orders are regular insert streams, but the third one actually indicates that there is a cancellation of an order. So the query has to produce a pair of update events. what you see is that first there's an update before, which is expressed as a -u, which is retracting the result of the 50 heads. And secondly, you see an update after, which is the +u. That's the event that actually replaces the old entry with a new one showing the 35 heads. There is one fun thing to know about this, is that if in Flink you define the concept of a primary key, it means that your system can do upserts, your sync supports upserts, because you only have one key, and therefore you can eliminate 50% of the traffic that you're actually generating out of Flink, because at that point you do not need to do the update before, because you're just upserting the new result. Now, exactly how the sync will perform the retraction and the update depends on the combination of the connector that you're using for your sync and the sync format. It could be something like a JDBC database. You could be using a Kafka topic with a Debezium format. And all in all, the table is the materialized result of your changelog stream. What is very well important to know is that Flink itself is not a database. The data does not remain in Flink, and you need to basically store your data always in another system. Let's dive a little bit deeper into Flink's table API architecture. As I've already mentioned, the table API interface are basically accessible in 3 languages. You have Java, Python, and SQL. SQL and the table API share the same architecture, same concepts. And under the hood, Apache Flink uses the Apache Calcite framework for things like parsing and validating of the declarative logic that you are submitting. And there are a couple of key components in the table API architecture and design. If we're looking at the components that are here on screen, all of these components work together to provide you with that powerful, flexible system that Flink is. At first off, at the top, you have the table environment, and the table environment is the central entry point for all table API operations. It creates and manages tables, it registers dynamic table sources and dynamic table sinks, and it interacts with the catalog. Tables in Flink represent both static and streaming data, and you can create them from various sources or as the result of queries, of course. The dynamic table source defines access to the external data for reading, and the dynamic table sink defines how to emit results into the external systems. And both of them, of course, support bounded and unbounded data so that you can have that unified batch and stream scenario incorporated. Now, the catalog in Flink is all about managing metadata for tables and functions, and it provides that information to the table environment, tables, and dynamic table sources and sink. And dynamic tables, as I've just shown in the slide before, they are continuously evolving with new data. And the connectors implement the actual logic for reading from sources and writing to sinks, and they work, of course, with the dynamic table source and dynamic table sink. And this diagram is very much illustrating how all of these components interact together. Central table environment managing the tables, registering the sources and sinks, and the tables actually read from these sources and write to the sinks, and the catalog provides information or metadata throughout the entire system. So if I submit a table API application, what actually happens? Let me take you on a tour in Flink's table API planning. So if I have a table API logic, or SQL, because it works exactly the same, what happens is that Flink breaks it down into a structured form that it can work with. It's like taking a sentence and parsing it into its grammatical components. And at this stage, it's also the moment where Flink checks if everything in your query actually makes sense. Are your table names correct? Do the columns that you're referring to actually exist? Do you have a valid syntax? So it's all about parsing and validation. And internally, this results in SQL nodes and rel nodes in Flink. And the next step is actually where Flink tries to get clever. It looks at the query that you're submitting and potentially tries to rewrite it in a way to make it more efficient, but without changing, of course, what the query should actually do. For example, if you use something like a subquery, Flink might realize that it could turn it into a join instead, which could be faster in terms of actually getting the results out of that. This is basically the first round of logical rewrites, and it results in optimized rel nodes. The third one is something that is quite common in batch processing, which is a cost-based optimization. You can have that Flink tries to estimate which way of executing the query will actually be the fastest, It can consider things like how much data does it think it will need to process, how different operations might be able to work together efficiently, kind of like trying to be a chess player that tries to think several moves ahead in order to find the best strategy to get the result done. Then there's a step where Flink applies more specific rules that knows that are working particularly well for this type of processing data. Might figure things out like the best way to handle time-based operations or rearranging parts of the query to work better in Flink's streaming model. And at the last step, Flink transforms this entirely optimized logical plan into a physical plan, basically the concrete steps that specify exactly how the data will be processed, moved around, and computed when it's being executed in Flink's runtime. And in this entire process, Flink is trying to balance different factors, like how to minimize data movement, how to parallelize operations, how should I use memory efficiently, and everything. So this is taking your high-level declarative way of what you want to do with the data and figuring out all of the nitty-gritty details of how to do this as efficiently as possible. Now, if you would like to see the result of such a thing, you can use Explain. And Explain is a powerful feature, and it allows you to easily see the execution graph, which is basically that last step from the planning phase. And in this is a code example where it's a very simple pipeline. It's using statically defined data with the from values. I'm going to do an insert into to make sure that it's being sent into a table. And print explain generates the execution plan explanation. And if you want to understand the output, you basically see a tree-like structure of operations where the stream physical sync is actually the final output operation where the data is being synced into. The union is the combination of different data streams. The calc is performing the calculations of transformations, and the physical values is actually the representation of your input data. Now, if your plan results in a different changelog mode than append only or insert only, it would show that here too. Like if I would have the example from the stream table duality thing, where you would have an updating query, you would see things like upsertions or potentially deletions in the plan explained as well. All right, now I'm going to hope that this is going to work, but I have an example of one level deeper, which is the compile plan. Let's see if this is going to work. I'm going to make it full screen. All right. So this is an example of all the low-level details that you can do. It's using one of the recipes, which I will link at in the end. This is an example of a deduplication query, and that has a test in there that prints the compiled plan. And the compiled plan is the fully optimized execution plan, but it also includes all the details necessary for executing the logic. It contains details like tables, columns, data types, connector options, the operations that are happening, query configurations, like state time to live, Flink configuration options, and everything. And compile plans are actually also a key thing if you want to upgrade your Flink Table API application from one Flink version to another. I'm going to see if I can switch back to the next one. Oh, I first need to stop this. All right, we'll get there. I hope. Okay. There we go. All right, it's going to be fun with switching. Anyway, now that we have an understanding of Flink's architecture, what can you actually do with the Table API? This is a slide that is representing, let's say, the wide array of operators that are available in the Table API. Everything that's marked with a purple dot, it represents an operation that exists in both batch and in streaming. For example, we have sort, which is a common operation that you can use both in both modes. And orange operators are specifically for stream processing. An example is a window aggregate, which is being used for calculating moving averages, for example, or summarizing sensor data in 5-minute intervals for IoT devices. Another example is a watermark assigner, because a watermark assigner is the key part in Flink that's needed to track the progress of event time throughout the system, and that is necessary to emit incremental results, handling out-of-order data and late data. And green dots represent batch-specific optimizations. A hash join, for example, can be a more efficient join for large data sets. And most likely you will also recognize some of the names from the SQL world if you would look like a group aggregate that immediately represents or brings a similarity to mind on SQL's group by, which is something that you would typically use when you're doing an aggregation. And two of the operators that I actually want to highlight are the interval join and the temporal join. An interval join basically joins elements of two tables, say table A and table B. You have a common key in there, but you also add the condition where elements of table B have timestamps that lie in a relative time interval to the timestamps of elements in table A. So instead of having only a condition on the key, you add a time constraint in there as well. And temporal joins are specifically meant for performing time joins against a version table. In other words, to enrich table A with the value of table B at the moment in time. The most common example that everyone uses is where you have a stream of orders coming in with orders. And you have an order value in there which is in different currencies, and then you would have another version table which basically has the exchange rates for you, so you can actually see what is the monetary value for each of these orders in your own preferred currency. Well, next to all of these operators, there are more than 200 built-in functions in Flink's Table API and in SQL, and they cover basically a wide range of processing data needs. Key categories are around comparison, logical for all data filtering and conditions. You have arithmetic and string manipulations for your basic manipulations on that one. Temporal, which is all about time-based conditions, and conditional, of course, if you have something like a case statement or a switch perspective. There's also some more advanced stuff like doing type conversions, collections, JSON functions to manipulate JSON objects. It's all about handling complex data structures. And aggregate and window functions are specifically powerful when you're actually analyzing data. Now let's dive into the examples, given that I've shared a lot of dry content with you. Let's actually look at some of the stuff that is in action. I'll start off with an example of an Hello World application, which I'm going to loop as well. And this is a side-by-side example of the Table API in both Java and Python, Java on the left. It's just a simple Hello World exercise. What you first do is you create a table environment, which is that entry point for Table API operations. And then you create a table in a programmatic way. In this case, with the static Hello World values. And of course, you can also mix in SQL. And when you actually run this, it's being executed in this on a Flink cluster. In this case, it's Confluent Cloud. But this can, of course, also be your local SQL cluster. And when you actually see the results on screen, they are being shown as insert operations, as indicated is with the plus I. All right. Let's see if I can now switch. I really need to stop the video first. Second off, another example that I have to show for you. This is an example on catalogs, because catalogs, databases, tables, and schemas are another key part of Flink Table. This is an example that shows all tables in an examples catalog and in a marketplace database. And tables, of course, can be referenced using three-part identifiers, catalog, database, and object, like is defined in the SQL standard. And that is the first part of what is actually being demonstrated here on screen. And next up, you actually see the available catalogs. It sets examples as a current catalog, and it shows the available databases. Then you set marketplace as a current database. And when you do that, you can use a one-part identifier, an object name, to reference a table after setting a current catalog and database. Now this is all still fairly straightforward, not too complicated. It's so fun when it doesn't work as I intended to happen. Here's an example of just a simple example code that I have in here. As I've mentioned before, Flink is a unified batch and stream processor. Now in code you can have a bounded or a finite table, like specifying the static data. And in here you can use exactly the same filters as you can do in streaming. So the example that we have on the top part is filtering for all names that contain the letter E. Now, in the examples repository, there's also an example where you can use and run an unbounded query. That's a query that will never end because there might continuously be data that is coming in. And this example is doing an aggregation of the total time spent on the website per user ID. And since that's doing an aggregation, this results in a changelog stream with updates before and updates after, as you can see with the -u and the +u. And let me actually show you just an example of how to transform table objects. Here we have two data sources. We have an orders table from our catalog and a mock customers data, table. And this customers table is created with from elements. And we filter the order table on specific customers ID using the filter method. And the call function is used to reference columns, and the in checks for the membership of it. Then we modify the columns using add columns, rename columns, and drop columns. We round the price and we cast it to an integer. And then we perform an unbounded join between a customers and an orders table. And the join condition is specified again using that call function. And that final result that we're creating over here is just a join table with customer and order information. And we see columns like customer ID, name, email, order ID, but also the price rounded in there. This is an example that really shows the declarative nature of Flink's Table API. You can see how it's being used to chain operators like filtering, transforming, and joining tables all together. I do not know why it starts again with playing when I do this. All right, luckily there's only one more example, so only one time I'm going to mess it up. This is all about sending data to one or more tables because, of course, we just emitted stuff on screen, but you also want to actually emit it. We're going to create two target tables, price per product and price per customer. And this executes a pipeline. This executes a table pipeline, sorry for that. And it inserts that static sample data into the price per product table. And as we've seen with a bounded table, it's a bounded table, and therefore we can actually wait for that entire execution to be complete, that all of the data has been inserted. And then when we do that, we actually execute an asynchronous statement set. And a statement set is one of the operators in Flink that can be used to read from a table once, having a different filter, but then still sending the actual result of each of the different filtered results into multiple tables as well. And just for the sake of validation and demo purposes, this example reads and merges the data again from both tables. So you can actually see and verify the data insertion. And we use that by applying a union all, and therefore it combines the results of both tables in here. All right, so I've shown you a bunch of examples, wide variety of operators that you already have available. So what if the current operators and functions actually don't allow you to achieve your desired business logic? If you are in that situation, Flink has a wide variety of creating what we call user-defined functions. And this is a diagram that shows all of the UDF types that Flink has available, the input and the output characteristics. So we go from scalar functions, where the input and the output are both scalar functions. It's just a simple one-to-one transformation. You could have something like a complex calculation or conversion that you cannot cover with one of the built-in functions. When you're doing a table function, you can have a scalar input, but you can actually emit multiple rows. So it's a one-to-many transformation. One of the examples that you might have in here is XML parsing, where you're extracting multiple elements from a structured string into separate rows. You can also have an aggregate function. And in an aggregate function, you actually have an input of a group of rows, while the output is a single value. For example, something like geospatial clustering, where you're grouping geographical points into clusters together. With a table aggregate, you have as input a group, and your output can be multiple rows. And an async table is quite similar to a table function, but it allows and it supports asynchronous operations. This is quite typically used when you actually want to enrich your stream with information from an external source, like a REST endpoint, a JDBC call, or something like that. And then there are two specific user-defined types that are there from a Python point of view. You have Python UDFs, where, for example, you can leverage pandas for vectorized execution. You can implement scikit learn models with Flink. And vector UDFs are offering flexible vectorized processing. They typically give a higher performance than the non-vectorized UDF because there is less serialization and deserialization overhead. An example of a UDF is the one that I have on screen. This is an example scalar function UDF. This demonstrates the processing of BASON or binary JSON. And it does so because it takes a byte array input of BASON data. It uses the library to decode it into a BASON document. We then extract an ID from the structure, and it returns a Flink row object with the extracted ID and timestamp, therefore converting the external data into a Flink-compatible format. And important to note in here is the data type annotation. And this data type annotation is very important because it allows you to map, let's say, the incoming data back into Flink's type system that you have in there. And this is a typical UDF pattern. Of course, you can modify this to any data format of your choice. But there's one more thing before we actually wrap it up and go into Q&A. And that is a proposal about a new type of UDF that is out there. Perhaps you have seen yesterday's talk from my colleague Timo Walter about the past, current, and future state of SQL. If not, when the recording becomes available, I would highly recommend for you to watch it. And in that talk, he also brought up polymorphic table functions. Polymorphic table functions, the syntax already exists today in Flink open source. You can see it in the windowing functions. But the proposal for a full implementation for polymorphic table functions means that we're introducing a new type of UDF that allows enabling user-defined SQL and table API operators. An example that we have on screen is straight coming in from the SQL standard. This is a user-defined join. This is the way that you would express this in your SQL or in your table API application, for that matter. And the proposal that is out there is all about providing new primitives to access that allows you to give you access to the building blocks in Flink, like state and timers and your own custom logic, for that matter. And they are very much comparable to the process function that you have in Flink's DataStream API. And the idea of this is that this really is going to help with a lot of use cases where it's hard to provide a fluent declarative API, where we see it, for example, in SQL. If we're looking at the logic that is necessary for running a deduplication query in SQL, that is quite a cumbersome one, and it would be much cleaner to actually express that as a polymorphic table function. But given that a polymorphic table function will be comparable to the process function, this would basically give you the ability to build any event-driven application using Flink's table API. And with that, I would like to wrap it up. Thank you all very much for listening. In case you're interested in the example, the QR code basically brings you to the Linktree thing, which has the links to the various repositories. There's a table API Java examples repository, a table API Python examples repository, and there's specifically a Flink cookbook which has the recipe on the compiled plan. And if there's any more questions, I'm more than happy to try to answer them that you might have. Thank you.